There we go. Okay, so this is when we're talking about partial pressures and what pushes the gas. Once the air is in your lungs, what pushes the two gases the right directions, right? So think about concentration gradients, which even if you haven't had chemistry yet, you'd remember from physical science. Remember, if we have a high concentration of something in one place and across a membrane a low concentration, that thing, whatever it is going to want to like even out, right? That's that whole like homeostasis. Things want to diffuse across a membrane to get to the same level on both sides. So we have a super like simplified, like to the point of being silly kind of drawing here. Blake, this is my explanation of what's on page 465 in your book. But so what I want you to think about this one as being your lungs. That's why I drew lungs. This one represents the tissues all over the rest of your body. So, the bottom of your toe and in your brain and everywhere else. And then our circle here is our circulatory system. Okay, so when we take a breath in, the air that we breathe in has a mix of oxygen and carbon dioxide in it, right? And it mixes with the air that's already in your lungs still from that residual volume we were talking about earlier. And once that mixing has happened, the concentration, in a sense, and your book talks about how this is called partial pressure of a gas. Think of it like concentration, though. It's measured in millimeters of mercury. So mmHg, that's a pressure measurement, right? I just didn't feel like writing that over and over, but all of them are in millimeters mercury. So the air that I breathe in, once it's mixed with the old air that was still hanging out in my lungs, thank you, is 104 millimeters mercury of oxygen, that's the pressure or the concentration, and 40 millimeters mercury of carbon dioxide. Mm-hmm.
The carbon dioxide can only go up to 45, and then the oxygen drops to like 40 by the time it's done with this person, right?
Yeah, the range that changes in your body, in your blood from one place to another of carbon dioxide is a much smaller range than the way that it swings much wider for your oxygen.
So why is that?
Well, we'll come to that.
Okay.
So the air in my lungs, in my actual lung tissue, in my alveoli, is this mix, but the air that's in the capillaries that we're going to see in our lab, the oxygen in the blood in that capillary is down to 40 millimeters mercury. It's deoxygenated when it gets to my lungs, right? So it's down to 40. And my carbon dioxide, because it's been picking up waste from my whole body to bring it to the lungs, is higher at this point. It's 45. So if we know that things want to move across their diffusion gradient, they want to go from a high concentration to a low concentration, which direction will my oxygen move at this place? Right, it's going to move out of my lungs into my blood. And which direction will my carbon dioxide move? Right, out of the blood into the lungs. And because this is always moving, you pump all of your blood, your whole supply through your body about once a minute. So it's always fresh blood that's squishing through here. This number never really goes up, right? It keeps the gradient always stuck that way so that oxygen is always moving into your blood. Because as soon as this blood gets a better number, it's already moved along. And
is
fresh.
That like how it's always trying to even it out, but since it never evens out, it just keeps going?
It just keeps working, right. So by the time it's leaving your body and getting out to your tissues, it has initially gone up a little bit higher, but by the time it leaves your body, it's at 95 because first it's got to give up some of its oxygen to feed your actual lung tissue because those are living cells, so they need oxygen to actually work with. So by the time we get out of the lungs and into the body, systemic circulation, we're looking at 95 for oxygen. But your tissues have been using up the oxygen they had, so they're staying at about 40. So which way will my oxygen go now?
In.
Right, out of my bloodstream into my tissues. And then my carbon dioxide, I had gotten it nice and low down to 40. So you can see these things kind of even out, right? So these numbers match. I'd gotten my carbon dioxide down to about 40, but out of my tissues that have been doing cellular respiration constantly, they're up to about 45, which is going to push carbon dioxide which way?
To the bloodstream.
To the bloodstream, right. So that's why when we're like looking at diagrams of the circulatory system, we generally see I did these backwards. Usually red is used for oxygenated. But generally we would see how we represent things red or blue in the bloodstream, and we talk about those being oxygenated or deoxygenated. Like I said, I've done them backwards. I should have done oxygen in red. But that's why this side would be colored red, right? Although in my diagram it would be blue because I'm backwards. Because all through here I have a higher concentration of oxygen, and then all through here I have a higher concentration of carbon dioxide, because I've given up my oxygen and picked up carbon dioxide to return to my lungs and get rid of it. Okay? So this is really just all about concentration. It's going to, in general, God has created the world so that things move from higher to lower concentration. So then to answer your question about why it's such a small gradient, right?
Yeah, why it's such a big gradient.
Right. Right, it's a big gradient for oxygen and a small one for carbon dioxide. And the one for carbon dioxide, I don't know that this answers the why question, but it's a connected idea. What causes us to take our next breath, if you remember from your reading, is not that you need more oxygen, it's that you need to get rid of carbon dioxide. That's what actually triggers your brain to take the next breath. So you've got some control centers in your medulla oblongata and in your pons that help to regulate how deep of a breath you take and how often you take a breath. So that's called a hypercapnic drive. This is the normal drive. So hyper meaning high or too much, right? And capnic meaning carbon dioxide in the bloodstream. So too much carbon dioxide makes you take another breath, right? People who live though with lung disease and aren't able to adequately breathe and adequately blow off enough carbon dioxide on a regular basis, their brain eventually will say, well, we never managed to fix this problem. We're always short of breath. We always can't get rid of enough oxygen or enough carbon dioxide. So eventually their brain cells that control this will flip and start to do what's called a hypoxic drive. What do you think that is?
When there's not enough
Too little
oxygen.
Right.
Ooh.
So normally it's too much carbon dioxide that triggers the next breath, but if you live in that space all the time, like chronically, like from having COPD, then you flip to this too little oxygen drive. This becomes a big deal, like you were asking about clinical things earlier today. This becomes a big deal if you, for example, show up, maybe you have emphysema because you smoked a whole lot your whole life, right? So your brain has made this switch, but maybe you've got like a brand new nurse who just graduated and hasn't seen things go wrong before. And you come to the hospital, in the winter, maybe with pneumonia, and you can't get a good deep breath. And your nurse, meaning all the good in the world, throws some oxygen on you. Like, at a higher rate than what's in the air around you. Well, now she's given you more oxygen, but your body's used to using this to tell when it's time for another breath, right? So if suddenly this goes up, you're not hypoxic anymore.
So you won't need to take
So your brain says, oh, we're good. We don't need to breathe. And you can actually cause people, it's rare, but you can cause people to have even more trouble or even stop breathing if their body is in hypoxic drive. That would never happen in a normal, healthy person with healthy young lungs who also just is now having a hard time breathing because of pneumonia or something.
How can you tell if that switch is happening?
There's not like a particular thing that I know of that you can assess. It's kind of knowing their history. So if you know that this person has a long-term lung disease, then you would just proceed with caution. And that doesn't mean you would never use oxygen on them, but you wouldn't put it on and crank it really high, the way you could on younger people to get more oxygen in quickly. So.
You could just give them oxygen, see if they pass out.
I guess you could.
If they do,
Of course, then you get to do some CPR, and that's super fun. Along these levels, I just wanted to show you really quickly these equations so this is page 468. This is what those cells in your brain are monitoring all the time. So you've got two sets of equations on the book, but we can write them this way, and I think that this illustrates what's actually going on a little bit better. You have these two sets of reversible reactions. Think of them kind of like a seesaw, or teeter-totter. So depending on how much cellular respiration, how much work my muscles and my tissues are doing, I'm going to create CO2 and dump it into my bloodstream, like we did up here, right? As I dump it into my bloodstream, it reacts with the water that's in my bloodstream. You just have water there, right? Water molecules. And it creates carbonic acid. That's what this is. Carbonic acid dissociates, it loses a hydrogen ion and creates this carbonate molecule and free hydrogen ions. Your brain is always looking at these hydrogen ions to see like how many are there, and because extra hydrogen means that you're becoming more acidic. So as it's checking to see like what's your acid-base balance like, are there too many hydrogen ions? If there are, it's going to respond by getting rid of more CO2. Because just like these, with our trying to find the balance, trying to move across a gradient, this equation, these two equations that are stuck together are always trying to balance themselves like a teeter-totter, right? So if this gets too high, we're going to take out some of this to force our chemical reaction to move this way, to try and balance out how much CO2 I have. Mm-hmm.
So hydrogen makes you more acidic, and then what makes you more basic?
Is that a hydroxide? It's basically the two parts of water. So like hydrogen by themselves makes you more basic. I'm gonna say this is called a hydroxide ion.
Does hydrogen make you more basic?
I'm sorry, more acidic.
Okay.
Sorry. I want to say this is called a hydroxide ion.
Okay.
Makes you more basic.
So
Do you remember from chemistry what these are? Yeah, that's okay.
So Starbucks isn't the only thing that makes you basic?
No.
Okay.
I feel like if you drink enough coffee, you might end up acidic.
Acidic, not basic?
Maybe. I'm not sure. So your body, if you make too much carbon dioxide, right, your body is, if you have an increase of this, you're going to have an increase moving this direction to create more of this carbonic acid. And as you create more of that, it creates pressure to push it into bicarbonate ions, and hydrogen ions. That's when your brain figures out that there's too much carbon dioxide because this side of the equation has gone too far. So to tip it back this way, it's going to remove carbon dioxide. To remove carbon dioxide, it's going to make you breathe faster, right? Because every breath you take is going to do more of this process and push off a bunch of carbon dioxide. So one way that we can tell in the hospital that somebody's starting to get into a problem with their acid-base balance is when we see people start to breathe really deep, really fast, without being in a panic mode, right? Like there are certain times that like our psychology affects the way that we breathe, but this would be like if somebody's unconscious and breathing too deep, too fast, then we know something's wrong with their acid-base balance. So your lungs help to regulate your acid and base balance, but they're actually the second line. So they're a good short-term quick fix, but they're not good for like day-to-day overall balance. We'll learn about that when we get to kidneys next week. Wow, we're almost done. Okay, so let's pause here. Blake, I'll move that closer. So this is what we have here. I'm gonna include the slide that we're about to look at, in the email so that you can do the micro lab as well.
See, look, Blake's basically having a one-on-one class. It's not that awkward.
It's awkward for me when it's one-on-one here.
Okay, I see.
I don't care if he watches it later. Okay, so I'll have another video in a minute.